Allons-y. Donc bonjour à tous. Donc nous allons avoir donc un web séminaire, donc le deuxième web séminaire de l'année organisé par le réseau des plasmas froids. Donc comme d'habitude, il va durer environ 50 minutes. Vous avez eu le lien envoyé par mail il y a quelques semaines et puis un rappel il y a 1 heure. Et à la suite de ce web séminaire, vous pourrez poser des questions donc sur la plateforme Slido. Donc n'hésitez pas à poser des questions durant le web séminaire et puis un petit peu après. Et donc ce web séminaire va être donné par Monica Magureanu en anglais, donc qui est Senior Researcher donc in the National Institute for Laser, Plasma and Radiation Physics in Bucharest, en Roumanie. Donc voilà, je te laisse la parole.
Thank you for the introduction. Good morning, everyone. I'd like to start by thanking my friends here in Gramy for their hospitality, and among them, of course, Hervé for the opportunity to give this talk. So the talk concerns the degradation of organic pollutants in water by non-thermal plasma. And I will give 2 examples, the degradation of pharmaceutical compounds and the degradation of pesticides. So regarding pharmaceuticals, I will say a few words about the sources of these compounds in water. Then I will enumerate some of the pharmaceuticals most commonly found in the environment, and I will talk about their degradation by plasma. First, I'll show a few configurations of plasma reactors, and then I will talk about the most important parameters that are followed in these cases, the removal of the target compounds and the mineralization. And it is also important to increase the biodegradability of the treated effluent and to reduce the toxicity. Correlated with the toxicity, it's important to identify the degradation products, because they can also be harmful, and in some cases even more harmful than the parent compounds. And of course, it's also important to follow the degradation pathways and to understand the mechanisms. This is a picture that I took at home. These are the medicine that my mother takes either on a regular basis or occasionally. And like her, there are many, many patients with 1 or 2 chronic diseases. So it's no wonder that the consumption of pharmaceuticals is huge. And in fact, it has been rising constantly during the last years. And this is due to several reasons, such as the population growth and the inverting age structure, as well as the appearance of new target age groups, the discovery of new drugs or of new uses for the existing ones. So as you see, the figures are quite alarming. There are thousands or even tens of thousands of tons of pharmaceuticals that are consumed each year. And of course, this leads to an increased risk of water contamination. Some of these compounds are persistent and accumulate in the environment. Then there is also the risk of bioaccumulation. The toxicity of pharmaceuticals is quite a big problem, and not only of the parent compound, but also of their metabolites and degradation products. Regarding aquatic species, they are exposed to a cocktail of such substances, even if the individual concentrations can be relatively small and maybe individually they have no effect. In mixtures, the effects can be additive, and there is limited knowledge on this global effect on aquatic species. Regarding human health, it is more or less the same problem. So humans can be exposed to pharmaceuticals through drinking water or through food contaminated with, irrigated with contaminated water. So again, we have exposure to trace amounts of pharmaceuticals over a long time. So the effects again can be quite unpredictable. Regarding the sources of pharmaceutical compounds in water, so excretion is considered as the most important source of water contamination, So excreted human pharmaceuticals from households or hospitals pass through the sewage network, and then they reach wastewater treatment plants. There, some of them are degraded, but not all of them, and many are not completely eliminated during this treatment, so they are transported and contaminate surface water. Then veterinary pharmaceuticals firstly contaminate soil, mainly by manure spreading in the fields, and then by runoff and leaching they reach surface and groundwater. Another source of water contamination is the sludge from the wastewater treatment plants that may also contain undegraded pharmaceuticals and is used as fertilizer, so it has basically the same fate. Disposal of unused medicine is also a source of water pollution. So these medicines are deposited in landfills, and then by leaching they can reach groundwater. And finally, we have also waste disposal from pharmaceutical manufacturing facilities or accidental spillings during the manufacturing or the distribution process. So finally, the contaminated ground and surface water reach drinking water treatment plants, but some of the pharmaceuticals can still escape this treatment, and then they end up in drinking water. Here I have a graph with the removal efficiency of some pharmaceuticals, many in fact, in a wastewater treatment plant. So you probably don't see their names because the letters are quite small, but what is important to see is that indeed there are a few pharmaceuticals that are completely eliminated during classical treatment. There are some that are partially eliminated, and there are also many where the removal efficiency, as you see, is negative, and this means that the concentration in the effluent is actually larger than in the influent. This has been observed in several studies and has been explained, for instance, by sampling uncertainties or by the presence of chemical transformation products or by adsorption-desorption processes. So the literature tells us that the total concentration of pharmaceuticals in the influent of wastewater treatment plants is of the order of some tens of micrograms per liter. And if we look at hospital effluents, the concentrations are much larger. So only for antibiotics, there are tens to hundreds of micrograms per liter in the hospital effluent, and for anti-inflammatories, the concentrations go up to milligram per liter range. And then there is a lot of research focused on dedicated treatments for hospital wastewater. So the idea is to treat the hospital wastewater directly at the source, separately from municipal wastewater. And this map illustrates such research. It's taken from a relatively recent review, and it covers 2 decades of research worldwide. Of course, classical treatments are investigated, but also advanced oxidation processes, such as ozone combined with UV radiation or with hydrogen peroxide and UV phantom and photophantom processes and so on. And I believe it's a good idea to add non-thermal plasma on such a map because similarly with the other more investigated up to now advanced oxidation processes, non-thermal plasma can generate highly reactive species, such as the OH radical, which is a powerful oxidizer and is quite non-selective, so it reacts with most organic compounds in the liquid. And an advantage of plasma as compared to the other advanced oxidation processes is that it doesn't need oxidizers from an external source because it generates them directly in situ. Here I've made a list of the pharmaceuticals that are most commonly found in the environment. I've tried to classify them according to their therapeutic use. So we have antibiotics. The main problem with antibiotics is that antibiotic-resistant bacteria can emerge. Then we have also non-steroidal anti-inflammatory drugs. In this case, for some of these compounds, the removal in wastewater treatment plants can be quite efficient. However, the consumption is very high, and then there is, in the environment, there is always a background concentration, so they are pseudo-persistent compounds. We have the class of antihypertensives. In this case, many of these compounds have very low removal rates by classical treatment. Then we have also lipid regulators, antidepressants, anticonvulsants. Carbamazepine is another example of a very recalcitrant compound. And we have also hormones. In this case, the problem is that hormones can affect negatively the aquatic species even at very low doses. And there are classes of compounds that I did not draw here, such as anti-cancer drugs or, for instance, contrast media and so on. So I marked with yellow the pharmaceuticals that have been detected even in drinking water, and I've marked with pink the pharmaceuticals that have been investigated by non-thermal plasma. And now I'd like to move to the design of plasma reactors, and I will start with discharges in liquid. For instance, this pulsed corona discharge generated directly in liquid in wire-to-cylinder configuration. It is used by a research group in INP Greifswald, and as you see, it looks quite nice. It extends almost in the entire volume of the liquid, and it has been used to degrade a number of pharmaceutical compounds belonging to different classes. What we also observe is that the efficiency or the G value. The G value is the amount of pharmaceutical destroyed per unit of energy, in this case per kilowatt hour energy introduced in the process. So as I said, the G value is relatively small, but we have to take into account that the initial concentration was quite small, and then the authors decided to calculate the electrical energy per order, the amount of electrical energy required to reduce the concentration of pharmaceutical by 1 order of magnitude. Now I'll talk a little bit about the discharges in contact with liquid, and I'll start with discharges above liquid. This is a configuration that we are using for quite some time, a corona discharge above liquid, where the high voltage electrode is an array of 15-20 copper wires, very thin wires. So the discharge is generated in the gas phase. It starts at the wires and it propagates towards the surface of the liquid. Obviously, it's a filamentary discharge, as you see here. We have used it to degrade a number of pharmaceutical compounds and also some pesticides, as you will see in the following. A similar configuration is used in a research group in Padova, in the group of Cristina Paradisi. In this case, they are having a DBD, so they have a dielectric barrier between the two electrodes, and they have only 2 wires, and again they used it for the degradation of many substances, and among them pharmaceuticals and pesticides. Here you have an example for the antihypertensive verapamil. Another configuration of corona discharge above water is this one, a point-to-plate configuration in this case. Again, the discharge is filamentary. It starts at the point electrode and it propagates to the surface of the liquid. It was used to degrade several pharmaceuticals belonging to different classes. And what is remarkable is that this is one of the few studies at pilot scale with large volumes of liquid, 150 liters. They are also using real wastewater or spiked surface water. And the concentrations of pharmaceuticals are of the order of tens to hundreds of nanograms per liter. So they are basically the concentrations that are found in the environment. In all these cases, the depth of the liquid is about 5 millimeters, so several millimeters. And as we know, the penetration depth of the reactive species generated in the plasma into the liquid is quite small. So people thought about reducing the depth of the liquid, or in fact increasing the ratio of the surface to volume. And configurations like this one have been developed. This is a dielectric barrier discharge with liquid falling film. It is used by a research group in Belgrade. So as you see, it's a cylindrical DBD configuration. The liquid is pumped through the inner electrode and then falls as a thin film on the surface of the inner electrode. And the discharge is here, again, in the gas phase and in contact with the liquid. There is also a nice planar configuration developed in a research group in Germany, also with liquid falling film. And we are also using something similar to this one, but the liquid is pumped from above. And another configuration is this one, the wetted wall corona, and in this case there is a wire electrode and the liquid falls as a thin film on the inner surface of the outer electrode. Another nice configuration is this one, the corona with liquid droplets. It's a pulsed corona discharge. Which is generated at the wires. It's similar with an electrostatic precipitator, in fact. So the plasma is, as you see here, generated close to the wires, and the liquid falls as droplets or small jets through the plasma zone. Then there is quite a large contact area between the plasma and the liquid. And they are quite successful. They obtain very high removal efficiency due to this efficient mass transfer of the species to the liquid. And from what I know, they recently patented this configuration, and they are using it for real hospital wastewater. We have been using for a while a configuration where we combine plasma and ozonation. In fact, it's not really ozonation, it's more like gas recycling, because we are using the gas generated in the plasma, which contains quite a lot of ozone, and we bubble it through the solution that is contained in a solution reservoir. So we have continuous circulation of the solution between the plasma reactor and the reservoir, and again the bubbling of the gas containing ozone through this solution reservoir. And we had a look at the ozone that is formed in the gas phase, and as you see, there are quite large concentrations This is the case when we have water in the reactor, but when we have only the plasma and not the bubbling, there is very little consumption of this ozone. So most of it just passes unreacted or without having any reaction, in fact. So then we thought about this bubbling, and with the bubbling in the first few minutes, all the ozone that is generated in the plasma is basically consumed in reactions with the organic molecules. And so here we have the ozone consumption, and only after the organic compound is completely removed, the consumption of ozone decreases significantly. And as you will see further on, this combination of plasma with ozonation was found to considerably improve the removal efficiency of the organic pollutants. And now I'd like to talk about the removal efficiency and the removal itself. So the removal is given, of course, by this formula, and the removal efficiency, as I said before, it's the amount of pollutant that is removed per unit of energy introduced in the process. And I have here a few examples for ibuprofen. This is a non-steroidal anti-inflammatory drug. And as you see, complete removal can be obtained for various input energies. This is again the removal as a function of the energy dose. And here we have a comparison of several discharge configurations and the results. So what we can see is that in lab studies, usually the concentration is of some tens of milligrams per liter. This is obviously orders of magnitude higher than what is actually found in wastewater. Then the volumes are generally small, hundreds of milliliters, with this exception that I told you about of the corona with droplets. The power introduced in the discharge can vary quite in a large range. And eventually, sooner or later, the removal can be quite high, or even complete removal can be obtained. But the energy yields, the efficiency varies again quite widely. So we can have quite low removal efficiency, such as in the corona directly in liquid, then removals of below 10 anyway gram per kilowatt hour, and relatively high removals such as 28 or 26 that we have obtained. In this case, where there is a good mass transfer of the species from the plasma to the liquid. This is another example. This is quite a good energy efficiency, 100 gram per kilowatt hour. We have obtained this in a DBD with liquid falling film combined with ozonation. So these are the results for amoxicillin, and we had also some tens of gram per kilowatt hour for other beta-lactam antibiotics such as oxacillin. And this is the comparison between plasma alone and plasma ozonation. We've done these experiments in the corona above liquid, again combined with ozonation, and the target compound was methylparaben. Methylparaben is actually not a pharmaceutical, but it is in fact a preservative, and it's found in many pharmaceutical formulations. So as you see, these are the results obtained by plasma alone, and the degradation becomes much faster for plasma ozonation. A few words about the mineralization. So mineralization means the complete elimination of the organic compounds to produce carbon dioxide and water, and eventually some inorganic compounds. We can determine this by total organic carbon analysis. This is very useful, especially for multi-component solutions, because it's a non-specific measure of all the organic compounds in a sample. And what we can see in these two examples is, first of all, that as we expected, the mineralization is much, much slower than the degradation, the removal of the parent compound, obviously, because this is a gradual process. The molecule becomes smaller and smaller by these degradation steps. And then again, there is the comparison between plasma alone and plasma ozonation. So this is effective not even for the removal, but also for mineralization. As you see here, we have after 60 minutes of treatment, about 30% removal of the total organic carbon while in the plasma, while by plasma ozonation we obtain much larger figures for the mineralization. A few words about the biodegradability as well. So biodegradability is given by this ratio of the biological oxygen demand over chemical oxygen demand. And what is important in these examples is that even if the mineralization is rather low, or if there is no mineralization, we can improve the biodegradability of the treated effluent by non-thermal plasma. And toxicity tests, they are quite rare in the literature. They are done usually using test organisms such as Vibrio fischeri, Artemia salina, Daphnia magna, and so on. The important parameter is the LCIS 50, and this is the effluent concentration that is lethal to 50% of the test organisms. And as I said, there are very few toxicity studies, and I believe some more research efforts should be dedicated to this issue. A few words about the degradation products. So to identify the degradation products is quite a complicated thing. This is usually done by LCMS, liquid chromatography coupled with mass spectrometry. So the compounds are separated by chromatography, and then the identification of the compounds is done by MS. And sometimes even MSMS analysis is needed in order to be able to identify these compounds. So as I said, for me as a physicist, this problem is a bit complicated, and I'm very thankful to the chemists that are on my team and are doing all this job. So this is an example for enalapril. And as you see, there are several pathways for the degradation of enalapril. There is hydrolysis to yield enalaprilat, and then intramolecular dehydration to yield this diketopiperazine, which is a quite common degradation product of enalapril. And then there are also some other pathways. We have oxidation here, and again hydrolysis and so on. And we've tried to follow these compounds during the treatment. We have here the degradation of enalapril, which you see is quite slow. We need 120 minutes to completely eliminate it. And then the appearance of enalaprilat and diketopiperazine, this happens relatively fast after the plasma is started, and then they start again to be degraded as well. This is the case of enalaprilat, and diketo is formed from another source, but then is degraded again. This happens to most of the degradation products. So They are formed, as I said, soon after the plasma is started. They reach a maximum, and then they are degraded, and sooner or later they are completely eliminated. But there are also products that are formed later, and they still accumulate in the solution even for long treatment times. And now I will switch to pesticides. I'll say a few words about the fate of the pesticides in the environment, and then I will talk about their degradation by plasma and by combinations of plasma with other removal processes such as ozonation, adsorption, catalysis. I'll say a few words about the influence of the electrical circuit on the removal efficiency. A few words again about the degradation mechanisms, and something about toxicity tests in connection with the possible reuse of the treated water. So we can define pesticides as substances that are meant to prevent, control, or destroy pests. They can be classified according to the target organism. The most important are the herbicides, because they account to approximately 80% of the total pesticide used. And then, of course, there are also insecticides, fungicides, and so on. The problem is that all these compounds can be harmful and can affect non-target organisms as well. They can also be classified by the chemical family. And I have here a few of the most important such families and a few examples for each of them. So for the organochlorines, the most famous is DDT. Aldrin is also quite well known. Then there are the carbamates. They are organic compounds derived from the carbamic acid, which you see here. The general formula is here. And here we have aldicarb, which is one of the most important of this class. Organophosphates, which are esters of the phosphoric acids, and as examples, parathion and malathion. Then the phenoxy family, they are carboxylic acids with a phenoxy group. And 2,4-D is one of the most widely used and most widely investigated. And the triazine family, they are compounds with heterocycles containing nitrogen, as in atrazine, simazine, and so on. So what happens when the pesticide is put in the fields? So adsorption can happen, and this depends on the soil properties and on the chemical properties of the pesticide. Then we can have leaching in case of heavy rain. This again depends on the soil properties, on the chemical properties of the pesticide, and of course on the volume of the water flow, and it leads to the contamination of groundwater. We can have also runoff, and this is the transport of the pesticides into the surface water. The pesticides in soil can be degraded by microorganisms. They can also be degraded chemically by various reactions such as hydrolysis, oxidation, reduction, and so on. And volatilization can also occur. So it looks like once they're applied in the fields, there is little we can do to prevent water pollution with these compounds. However, there are also other sources of pollution, such as manufacturing facilities or equipment rinsing operations, and in this kind of wastewater, the concentration of pollutants is very high, some hundreds of milligrams per liter, and the volume is relatively low, and then plasma could be used in such a situation. So these are some results that we have obtained with our plasma ozonation configuration for the degradation of 2,4-D. And these are the results obtained with plasma alone. The blue one is with ozone treatment alone, and the plasma ozonation clearly gives better results. So the degradation is faster and more efficient. And we believe that this improvement in efficiency is due to the reaction of the two long-lived species generated in the plasma, ozone and hydrogen peroxide. This reaction is called the peroxone reaction or the peroxone process, and it leads to the formation of OH radicals. So we have the OH radicals generated in the plasma, and as an extra source of OH radicals, we have this peroxone process in case of plasma ozonation. And indeed, here you see the concentration of OH in the plasma, and in the plasma ozonation configuration, the concentration is about 2 times higher. Another combination of plasma with other removal processes, in this case with adsorption, is shown here. This is a configuration used by a research group in Ghent, in Belgium. So they're using the adsorption on a nanofiber polyamide membrane in order to increase the local concentration of a pollutant close to the plasma zone. And they have observed that the removal is better in case of plasma adsorption, and the G50, the efficiency, is about 2 times higher when using plasma adsorption as compared to plasma alone. Another possibility is to use catalysts. This has been investigated for quite some time. And the iron catalysts are the most famous because they can decompose hydrogen peroxide generated in the plasma to form OH radicals. This is called the Fenton reaction. And these are some results. They are obtained in the DBD with planar configuration with liquid falling film that I talked about before. And as you see, again, the results are better when using plasma catalysis as compared to plasma alone, which is the red data points. Another result, also in a DVD with liquid falling film, in this case the coaxial version, is this one. So again, the plasma results are here, and the results with plasma combined with iron catalysts are significantly better. And it seems also that the amount of catalyst is important, and optimization can still be made. Other catalysts have been investigated as well, for instance, manganese and cobalt, which are well-known ozone decomposition catalysts, in the same idea to generate OH radicals. And again, the results with plasma catalysis appear to be better than with plasma alone. There is also some slight influence of the amount of catalyst. But comparing the manganese and cobalt with the iron catalyst, it appears that iron is still the best. A few words about the influence of the electrical circuit on the degradation efficiency. So these are results obtained in a corona above liquid, either in negative DC or with positive DC, or in a DBD configuration. They are obtained by the group in Padova. And obviously, the best results are obtained with the negative DC corona. they are better as compared to the positive DC and even with the DBD reactor. And these results have been compared and have been explained, in fact, by the more efficient generation of reactive species with this electrical circuit. You see here the concentration of OH radicals, of hydrogen peroxide, of ozone in the liquid and in the gas phase. And in all cases, the reactive species concentrations are higher in the negative DC corona than in the other configurations. We have also tried to improve the efficiency by tuning the discharge pulse duration. You know that we have this pulsed corona discharge above liquid, and we changed the pulse duration between almost 500 nanoseconds and about 50 nanoseconds. And the decrease in concentration is shown here as a function of treatment time. So as you see, there is not much difference between the results, except for the shortest pulses, the 55 nanoseconds, when indeed the removal slows down a little bit. And then we put the same data as a function of input energy. And here we can clearly see a difference. So we can see that we obtain the same removal, but at lower input energy if we reduce the pulse duration. And this means, of course, increased energy yield. And it's more or less a similar situation for the mineralization. So the results don't differ too much, except for the slower mineralization in case of the shortest pulses. So we managed to obtain like this about 1 order of magnitude increase in the energy efficiency for the removal of 2,4-D by reducing pulse duration in that range. And as I said, the degradation process slows down only for the shortest pulses. And we believe that this is due to the increased efficiency of the short pulses to generate reactive species, ozone and OH radicals. And we'll see this in the following. So this is the total amount of ozone generated during the experiments as a function of input energy for different pulse durations. So as the pulse duration is reduced, obviously ozone formation is formed with higher efficiency. With increasing pulse widths, there is a temperature rise, and this explains the slower ozone formation, because ozone is formed by this reaction and depends, the reaction rate constant depends on temperature in this way. And then with the temperature rise, there is also an enhanced ozone decomposition by various reactions, for instance, with atomic oxygen, with OH, with HO2. All of them depend on temperature and are favored at higher temperatures. With increasing pulse width, there is also an increase in hydrogen, in water vapor, and this obviously leads to less efficient ozone formation. Then regarding the OH, we have also plotted here the OH for the various pulse duration as a function of input energy, and again it's more efficient to form OH with short pulses. We believe that this is due to recombination of OH radicals to form hydrogen peroxide. In case of long pulses, the concentration of OH is higher than the probability for this reaction to happen increases as well. And as a proof, we have also the results on hydrogen peroxide, which don't depend at all on the pulse duration. they depend only on the input energy. And by dividing this data, we can indeed show that there is a larger proportion of OH radicals that recombine to form hydrogen peroxide in case of long discharge pulses. I will not go into details regarding the degradation products because I talked about this previously. So anyway, it is clear that the degradation products and the degradation mechanism depend on the chemical structure of the organic compound. So if we have compounds with more or less similar structure, the steps of the degradation will be similar. If they're different, of course, different steps will happen. Then the degradation products depend on the gas in case of the discharges above liquid. So obviously, in case of argon, for instance, we have only OH radical attacks of hydroxylation will be favored, while in case of oxygen discharges, we'll have oxidation, which dominates, and in case of air, nitrogen-containing products can also be detected. The evolution of the degradation products this is something similar that I showed before in case of the pesticides. So the degradation products start to be formed almost immediately after the discharge is ignited, and then they reach a maximum and are degraded in some time. However, this time is quite long, so mineralization is very time and energy consuming. So it will be good to look at these products to see how toxic they are and to stop somewhere on the way when the treated effluent is not harmful anymore to the environment. So in this case, toxicity tests, I'm saying this again, are very important. About the toxicity of plasma-treated water, I was quite skeptical, not only because they contain all these degradation products, which can or cannot be toxic, but they contain also some oxidizing species, such as residual ozone or hydrogen peroxide or other oxidizers, and some of them are very toxic. So it would be a good idea to try to remove them from the treated solutions. So anyway, there are studies that show that the toxicity can be decreased by non-thermal plasma, such as in this case. So with increasing plasma treatment, the toxicity first increases, probably due to the formation of degradation products, but then it starts to decrease, and as you see, at the end of only 10 minutes, the toxicity is much lower than the initial values. And there are some other studies that again claim to obtain low toxic or non-toxic plasma-treated solutions. But again, there are very few studies on this topic. We have tried to look at the toxicity to plants. So we have here an example for 2,4-D. These are tomato seeds, which are watered with tap water with this pesticide. Tap water with pesticide treated for 2 minutes, 5 minutes, 40 and 60 minutes, and clean tap water. So it's clear if we compare these two pictures that the pesticide inhibits growth of the plants the roots are very small and the plants after some time die. This is more or less the same in case of plasma-treated solutions for short treatment times, 2 to 5 minutes. But then after the pesticide is eliminated, this is after about 20 minutes, the plants start to grow in a similar manner with the ones watered with clean tap water. And we've measured the roots and the sprouts and compared them, and they look similar after 20 minutes of treatment of the solution. However, from these pictures and up to saying that plasma-treated wastewater might be used for irrigation, it's quite a long way, because of course a thorough analysis of the tomatoes in this case should be done to ensure that they are safe for consumption. And now I would like to summarize. So the good news is that recalcitrant pollutants can be successfully degraded by non-thermal plasma. How fast and how efficient this degradation is depends on a number of factors. It depends on the type of discharge, on its location, if it's in the gas or in the liquid. It depends also on the energy introduced in the plasma. Then the chemical structure of the compounds are very important. The solution characteristics as well, and the solution composition. This I did not talk about during the presentation. And the nature of the gas is important in case of discharges in contact with liquid. We can improve the efficiency to some extent by changing the reactor design in order to ensure a large contact area between the plasma and the liquid. We can also improve the electrical circuit by tuning the discharge parameters, and we can improve definitely by combination of plasma with other removal processes, as you saw, adsorption, ozonation, catalysis, or the Fenton process. Identification of the degradation products is important, firstly from a fundamental point of view in order to determine the degradation pathways and mechanisms, and also from a practical point of view to see if these products are toxic and how we can improve and adapt the treatment technique. Generally, the temporal evolution of the degradation products shows the further degradation of these products to small molecules in advanced oxidation states. But this does not always happen, as I showed in the results of Enel April. Mineralization is also very important. However, it's a slow process and energy consuming, and it should be correlated with the toxicity of the treated water. And regarding the reuse of plasma treated water for irrigation, as I said, it's important to analyze very well the quality of the products to see if they are safe for consumption. Thank you very much for your attention. This was all. And I have a few questions here. Okay, so the first one, for the development of the process, where can we imagine plasma treatment? Pollution sites upstream of treatment plants or at the level of these plants? Okay, so there are several ideas on this issue. It's the best is to treat the pollutants at the source. So if we're talking of pharmaceuticals, for instance, it would be good to treat the wastewater from the hospitals, or to treat the wastewater from the pharmaceutical manufacturing, because there we have a relatively low volume and we have large concentrations, and plasma has a chance to really to do something. So it will be upstream, definitely upstream of the treatment plants at the pollution site. Because afterwards then, if this wastewater goes to the municipal wastewater and it's collected together and then it's basically diluted, then we'll have a huge volume of water and we'll have lower amounts of pollutants. So I would say at the source we need to treat this wastewater. The second question is the mineralization can be the aims of the treatment of these organic compounds. So if I understand it right, you're asking if the mineralization is the final aim. Of course, the mineralization is an ideal. It would be really good to have only carbon dioxide and water. However, mineralization is not really economical because it takes a long, long time. So mineralization is only absolutely required in case of very toxic compounds. And for the rest, we should go with the degradation as far as the point where we don't observe any toxic compounds. Okay, and the next, how can we evaluate the toxicity of the treated water? So, as I said, there are a few toxicity tests with various kinds of organisms, such as Daphnia magna, for instance, or some other things, Vibrio fischeri, whatever. And they are grown. They are you need a control. So you put the species, one control with clean water, one with the plasma treated water, so the polluted water, and you compare them. Some of them will die, and hopefully they will be healthy enough to survive, and then you will know that the solution is not toxic anymore. In my opinion, you need some biologists to do this. I mean, it's quite difficult to grow these organisms in the lab if you you're not familiar with them, you're not friends with them. Okay, as the mineralization is not complete, is there some tests with bacteria used in water treatment plants after plasma treatment? Well, this is a question that that left me a bit wondering. So I'll skip it for now, and I will think about it later. I'll come back later. Okay. The next, for polluted water in environment by pesticides, for example, can we think to use NTP? If yes, how? So if the polluted water is already in the environment, let's say in a lake, it's quite difficult to think about using plasma because there will be a huge amount of water. And imagine pumping this in a plasma reactor, however big, and then putting it back into the lake. So I think it's quite complicated. It would be maybe more easy for groundwater. Then we can sort of pump it and indeed put it back. But it depends on how large the volumes are. As you saw already, Most of the studies are done at lab scales with very low volumes. And even the ones at pilot scale, it's something like hundreds of liters. So upscaling is one of the weak points of non-thermal plasma, indeed. Okay, so I think these were all the questions. At least I don't see any other. I don't see any other. Okay. Whoops, there are others. Okay. As the plasma is running in ambient air, what are the other species created in the liquid by the plasma? Do they play a role in the pollutant removal? So when the plasma is in air, besides the oxidizing species that I talked about more, the OH, the ozone and the hydrogen peroxide, will have the RNS reactive nitrogen species as well. We can have nitrates and nitrates in the water, and this can be sometimes a problem. But we can have also short-lived RNS, such as, for instance, the peroxynitrate, that is a powerful oxidizer as well. And they can also lead to the removal of such pollutants. Can we expect similar plasma devices to be efficient to degrade or remove micro or nanoplastics from wastewater? Micro or nanoplastics are really a problem. So I would say that for this kind of pollutants, something like filtration may be more appropriate, because these microplastics are solid materials. It is difficult to believe that plasma can be efficient in this case. I cannot say it for sure because I did not see any study. I thought about it at some point. Can it be? But I would say filtration would, or even maybe adsorption onto something, would be more appropriate in case of plastics. And the last one, or I don't know if it's the last one, but the last one here, how is the concentration of OH measured in the process? Yes, I should have mentioned this during my presentation. So OH measurement is not a trivial thing. We are using a chemical probe, 3-carboxycumarinic acid, to measure the concentration. This compound, 3-CCA, reacts with the OH and form another product. So OH is attached somewhere in the 3-CCA molecule and form a fluorescent product. And this product can be determined by HPLC, by liquid chromatography. However, we have to be a bit careful with it because usually there is a competition between the probe and the pollutant that you have, and then you need to have quite a lot of probe in order to measure correctly the OH, and then this fluorescent product that is formed and that is actually proportional to the concentration of OH can be degraded in plasma as well. So somehow you have to to be careful and to measure not only the concentration of the fluorescent product, but also the initial product, and to compare them and to look closely at the chromatograms so that you see that not other reaction products are formed and you are still in a range when you have, where you have accurate measurement. Okay, so I see nothing else, but you have a habit of producing more questions. So.
If you have, thank you, Monica, for this very nice, interesting presentation.
Thank you.
Merci d'avoir suivi donc ce web séminaire. Si vous avez d'autres questions, surtout n'hésitez pas à envoyer vos questions à Monica. Il y avait l'adresse mail, je crois, dans le premier slide, et de toute façon, il y avait l'adresse mail aussi dans les annonces qui ont été faites sur le forum, par exemple, il y a 1 heure, enfin il y a 2 heures maintenant. Vous pouvez revisionner donc ce web séminaire sur un lien qui vous sera communiqué sur le site du réseau. Donc allez voir sur le site du réseau. Et puis, juste avant de conclure, n'oubliez pas qu'il va y avoir 2 autres web séminaires d'ici la fin de l'année. Donc un d'Alexandre Nominé, donc le 9 décembre, qui portera sur l'apport des procédés plasma et laser pour la nanométallurgie hors équilibre. Donc ça, c'est le premier web séminaire. Le deuxième sera donné le 17 décembre à 14 h. Il y a des annonces qui vont être faites via le réseau, donc par Jean-Baptiste Sirven, donc du CEA, sur les LIPS, donc Laser Induced Breakdown Spectroscopy. Voilà. Je vous remercie à tous. On vous remercie.
Okay.